So I think at the end of class last time, we had just done member 1. Do you remember that? So let's start up our demo. So here's our demo. Up here we've got the what is it? ch3.pl, and down here let's do gprolog, and let's consult it. ch3.pl, period, and there it's consulted. Right? Now, what we're going to do next, so we did member last time. What we're going to do next is add. Now let's actually, I think we can take a look here at the definition of add. So add is it's called three-array, three. So this is add/3. There's 3 arguments, x, l, and L1, and here's the definition. L1 is L with X added at the beginning. And furthermore, we have another little note here that add X, L, L1 is not really needed because it's really just a single fact. So this is just kind of like a little exercise. Because it's a single fact, there's no need to really have it. But let me show you what add does. Let me give you a demo of add. If we do this, add A to the list 1, 2, 3, and then we have our last one be a variable, which is the most common, so we'll call it what. It's the most common situation. What should happen according to that definition up there? What should equal what? What should what equal? What should what match? I mean, what should match? What would make what match? Well, what does it say?
L1 is L with X
at the beginning. So what would what be? Yeah, A1, yeah, A1, 2, 3. Does everybody see what add does? Right? Okay. But now look, you can write add with a single fact. Now this is a real paradigm shift, you guys. I'm telling you. Does anybody know what the single fact would be for add? That's not even a rule. A rule is, add X, L, L1 if. This doesn't even have an if. This is just a single fact. Can you figure out what add would be? What the fact would be? This is the paradigm shift, you guys, if you can figure this out. How would you write add as a single fact? See, so that down here when I did add A, 1, 2, 3, what? It did this. Ah, excellente. So here, add XL. So, and then L1 is L with X as the car. Now, does everybody see that? This defines add. This single fact up here caused this to happen when we queried it like this. Is everybody with me? So that's add. All right. Now, there's another one that we're going to look at. The next one we're going to look at is called del. And del stands for delete. Okay? So L, and the definition of L of delete, DEL, is that L, so again, it's a 3-array, and it's delete X, L, L1. The specification is L1 is L with element X deleted. So let's do a couple things here. First of all, let's demo this with del A, and let's do A, B, A. For the list L, and then let's just do comma, and we'll just make the parameters match just for, okay, give them the same name. All right. So now, what should happen if L1 is ABAA with A deleted? What should it be? The list B. The list what? Oh, nice. Yeah, no, it's going to do them one at a time. So with the first, yeah. Oh, yeah, I see what you're saying. Yeah, yeah. The guess was that it would just be the list B. No, it doesn't remove all of them. It removes them each one at a time. So what would it be? The first list would be what?
BAA.
Yeah, it would be BAA. And then if I press semicolon to say it, see if there's another solution, what would it be? ABA. ABA. And then, but now, ABA, because those two A's in a row. And now, is there any other solution? And the answer is no. Ooh, that was a good, that might be kind of difficult to eliminate all of them. Well, maybe not. Ooh, that would make a good, exercise to eliminate all of them. So so what do you think? Let's see if we can figure out how to write del. It's a base case fact and a recursive rule. So what's the base case fact, do you think? What's the
X is 1
X is the first.
actually, should we can we del, maybe we should do this. Let's do del A from B, C, D. Maybe we should do this and then do L1. So what would happen here? It just fails. Okay, so what were you saying, do you think the base case is?
When X is the first element of the list.
If X is the first element of the list?
Then you just split it off.
Oh, right, right. So what would be, how would you set up the del for the base case? It would be,
Del X.
well, it's a base case fact, though.
Is it not?
It's not a base case rule, it's a base case fact. Ooh, this is interesting. Can you guys think about this?
Del X, comma, X bar L.
Del X, comma, X, comma, oh, del X, comma, and then
X bar L.
list X bar tail or whatever, and then what?
Tail.
Yeah. Now, do you see how this fact, now think about this. We're doing a paradigm shift here, you guys. Are you with me? Does everybody see how that works? Isn't it true? Okay, read the specification. It says L1 is L with element X deleted. Isn't it true that tail is X bar list X bar tail with X deleted? Do you see what I mean? So you just kind of like say what it is and you write it down. But now what about the recursive rule? How do you delete, what if it's not the first one? Then what is it? Then, now here comes the big, where do you put the complexity here? You put it in the first set of parentheses. Do you see this? So how is it that y bar tail 1 can be y bar tail with X deleted? Where the y's are the same y's. How is it that y bar tail 1 can be y bar tail with X deleted? If what? If, say it again? If X isn't, if tail 1 is,
If the list doesn't have X in it. No.
Would it be like tail 1
if,
have anything in it?
what do you mean doesn't have anything in it?
If X isn't the first element, so something else is the first element, and if X were to be deleted.
If something else,
Yeah.
yeah. Well, yeah, but if del, oh, come on. This is the paradigm shift. This, you guys, look, the thing we're struggling with, this is the paradigm shift. Now, look, you have to just say it. Look, what does del X LL1 mean? It's the third one is the what?
Is the
Second one with the what? With the first element, the first one deleted. All right. So how is it that y bar tail 1 is y bar tail with x deleted? That's true if what?
If X is in tail. If you delete X from the tail.
No, 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 no. Say it in the same order. Say it in the same order.
Tail 1.
If tail 1 is what?
Tail with X deleted.
Yes. Does that not make sense? Look. If tail 1 is tail with x deleted. Now, do you see how this... See, look, it's flipped here. The complexity is in what we would normally consider to be like the formal parameter, but it's not. This is unification. See, this is a paradigm shift. Does everybody see what we're saying? What we're saying is that y bar tail 1 is y bar tail with x deleted if tail 1 is tail with x deleted. Do you see? Where the y's are the same. Is everybody with me? This is a different paradigm. You got to think differently. You got to kind of like understand how to specify recursively. Do you see what I mean? You just have to kind of think about specifying recursively. Yeah? So that's our del. Okay, so now check this out. Insert x list bigger list. Now watch how insert works. Let's demo insert. Let's do insert A 1 2 3. Whoops, wrong bracket. 1 2 3 and L. Period. Now watch what insert does. Insert here. So here we go. Check it out. So what does it look like is happening? L is what? Or the third one is the what? Is the second one with the what?
The first one inserted.
First one inserted. But if I do another one, it's now again the third one is the second one with the first one inserted. The third one is the second one with the first one. The third, yeah. And now when it gets to the end, boom, then that's it. But it's inserted in. Does everybody see? So look. So here's the specification. The specification is bigger list is list with x inserted anywhere. Are you with me? Okay. So now let's see if we can do this one. This one is a single rule using del. It's a single rule using del. So because we already wrote del, delete, we already wrote delete, but isn't insert kind of like doing the opposite? So what is? So what is this? So it's a single rule, right? So it's an if. So we don't have a base case and a recursive case. We have an if, but just using this previous delete. So how do we write insert? Does anyone want to hazard a guess here? How would you do this? Well, in this case, we can say insert x list, bigger list. We don't have to have any, because we're just going to use del. So how is it that if, what was the specification for del? Del. What? Oh, say it again.
Del x bigger
List if, yeah. Look at that, sports fans. Because look, what is this del? It's saying list is what? Bigger list with x deleted. That's the same thing as what? Bigger list is what? List with x inserted. Do you see what I mean? And that's it. That's the one rule, and it did that. It did insert, like we just demoed. Is everybody with me on this? How could you fail to be impressed with this? This is just really cool. Now, check this out. How about, here we're going to have another version of member. So here's member 2 X list, only this time member is going to be defined in terms of del 3 with a single rule. Now remember how member, actually watch this. To set us up for this, check out this little demo. Let's do member 2. Let me show you how member 2 works. Let's do member 2 of A, and then let's have list BCD, just to see. So now what should happen here? Do you remember what member does? Should this succeed or fail? It should fail. Okay. And then on the other hand, if there is an A in here, then what should happen? It should succeed, right? And there's no more occurrences of A. And now let's take a look at how del works. Now, so how does del? What happens if we do del A, and then we do something like this, BAD, and then we do L. Now, so what should happen here?
Should be L is less BD.
Yes, so that's L is list BD, and there is no other one. But now check this out, you guys. How about if we do del A, and now we do BAD, right? Only this time we have an anonymous variable. Oh, sorry. You're right. Thanks for the correction. A, and then BAD. Only this time, you guys, we're going to have an anonymous variable. Now, what's going to happen here, do you think?
It doesn't return the list.
It doesn't return the list, but what does it do?
Say if it works.
Yeah, in fact, in this case, will it succeed? Yeah, okay, so it's true, so it succeeds, right? Are you with me? So does everybody see how the anonymous variable works? All right, then. Let's come up here. So how can we write, now does everybody understand what this del/3 means? That means it's a 3 array, 1, 2, 3. You see how del has 3 parameters, 1, 2, 3. So this is the prologue way of saying that del has 3 parameters, right? So you know there's function overloading. It's kind of like there's function overloading. You could have del 2 array del, you know. So that's part of the specification for del, or for any functor. Is everybody with me on this? Okay, so that's what the /3 is. But anyway, now member is going to be defined in terms of del 3 with a single rule. Because now how did member, so what's the rule? In other words, member 2 succeeds if what? If X is a member of list. If what? So X is a member of list if what? A single rule. X is a member of list if what? In terms of del now. In terms of delete. Come on, you guys. We just dun dun da 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 dun dun da 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 dun dun. Oh, say it again. Yeah. If you delete, now how does delete work? This is this with this deleted. So if what? If yes. So if this is this with this deleted, right? Is everybody clear on that? Is everybody good? Okay. Now, okay, let's take a little break here to go to the slides. The next thing we're going to do is we're going to take a look at at what a sublist is. Now, on this figure 3.4 from our book, he's got this concept of member. Now, and how does member, you know, when we wrote member, our own my member, you know, member's built in, but when we wrote my member, what did we say? We said that X is a member of what? Of L if what? How is it that X was a member? How is it that X is a member of L? If you did we do it with concatenate?
Yeah.
Mm-hmm.
So if you do what? If X is the what? If X is the car of L2 and you do what? Concatenate L with this, and L is the concatenation of this with this, right? And now what about but now don't you see that a sublist is the same thing? So what's the picture of sublist? Only this time S is not an element. It is itself a list, right? So what's the relationship between, in other words, when is S a sublist of L? If you do what with what? S is a sublist with L if you do what? If you do what? Concatenate anything with L2 to get L, and you do what? S with anything to get L2, right? And so the anythings are going to be anything, you know. All right, so let's remember that. S, so back to our demo. So let's remember that. S is a sublist of L if you concatenate anything with L2 to get L, and if you concatenate S with anything, you get L2. So now how do we do that? So here comes, now of course sublist is built in, so we're going to have to do my sublist. So list S is a sublist of list L. It's a single rule with two concatenate goals, right? Actually, before we do it, maybe we should demo it. Well, no, we don't need to demo it. Well, yes, we'll demo it. Okay, let's do my sublist. Let's do my, just to show you that it works, let's do my sublist C, D, E, and A, B, C, D, E, F. And now, should this succeed, yes or no? It should succeed. So that's true, because C, D, E is a sublist of A, B, C, D, E, F. So now, but it's a single rule with two conc 3 goals. So what is that? So what is that rule? This time we don't have to have the complexity in the first parameter, first set of parameters. So it's my sublist. What did we say? Conc underscore L1. What, but conc has 3.
Oh, yeah.
It's 3. It's conc 3/3, right? So we gotta have 3 things. So we said if you conc anything with L2 to get L. So how do we do that? We can see there's 3 things. If you conc anything with L2 to get L. So how do we do that? L. So conc blank L2 L, that's right. Okay. And if you conc what? S with anything. So how do we write that? Conc S blank L2. And that's it. And that my little demo of sublist, that's how that worked. Now, I think to see, you know, this seems like magic, doesn't it? I mean, this is a paradigm shift. It seems kind of like magic, how you can just save what it is and then it'll do it. But I've got a little demo here, and this is in the notes. You can run this yourself if you download the notes. But I have a little demo for how this would work. Because look, do you see this right here? It says my sublist CDE ABCDEF. Let's imagine that it comes up here, and this S is CDE, and this L is ABCDEF. What's the first thing it's going to do? It's going to do what? What's the very first thing it's going to do? It's going to conc what? Underscore with L2 to give L. So let's just go ahead and do that. Now watch. If we conc anything, this underscore with L2 to get A, B, C, D, E, F. Now, can you tell me what this will give us? Well, it will succeed, but how will it succeed? How? If you conc anything with L2 to get A, B, C, D, E, F, how can that be? How can that succeed? Multiple ways. And what do you think? What do you think the first way that it will succeed will be?
L2 is ABCD.
Yeah. Okay. So here, so L2 is ABCDEF, right? In which case, what's happening? The anonymous variable is what? Yeah. But now, what's another way that it can succeed? Now look. BCDEF. Are you with me? But then, what's another way it can succeed? CDEF, and what's another way? DEF, and what's another way? EF, and what's another way? F, and what's another way? Empty list, and then it won't succeed, right? But you see, there are these multiple, let's scroll up here. There are these multiple ways for this to succeed. So in the backtracking, what's the first, so when it does this, so now when it's doing my sublist SL with S being instantiated to CDE and L being instantiated to ABCDEF, what does it do? It does this. And it succeeds with L2 being what? Being what?
The whole rest.
ABCDEF. But then it's going to do what? But then it's going to conc what? CDE with anything to get what? To get that L2. But what's that going to do? Do you see what I'm saying? It's going to conc what? It's going to conc CDE, that's the S, are you with me? With what? With anything to give us what? L2. But that first L2 is going to be what? A, B, C, D, E, F. It's going to be A, B, C, D, E, F. Are you with me? And what's that going to do? Fail. But because it fails, no problemo, folks. If at first you don't succeed, try and try again. What is it going to do? Come back to here and do it with this one. Are you with me? But then when it does it with this one, what's going to happen? It's going to fail. But then it's going to do it with what? With this one. And what's going to happen when it does this one? It's going to succeed. Boom. There's the demo. Do you see how that works? Is everybody with me on that? So we can actually like put this in here and kind of like in our mind's eye, go through these traces. Okay. Now, the reason we called it my sublist is that there is a built-in sublist, and the thing of it is that they're not quite the same. Watch this. If I do sublist, now this is the built-in sublist. So if we do sublist S, and let's have this be ABC, what do you suppose? Now, what was the specification of sublist? It's that ABC, no what? S is a what?
Sublist of L, which would be ABC.
Which would be ABC. So this would be S is a sublist of ABC. So how can this succeed? Yeah, well, yeah, whatever. Yeah, you were right. But what are you going to do? List all the possibilities. And so what's going to happen? B, C, C, empty list, B, A, C, A, B, and then no, right? Unfortunately, what happens is if we do my sublist, all right, and we do, I don't actually have to go to the end to execute this line, but just to keep it the visual, check this out. It's this A, B, C, B, C. See, so what's it doing? It's doing what's being repeated here. See, it does all this. Did it actually get them all?
For this one, I think it only works if the letters are there in order.
Because there's no AC in there.
Oh, right, yeah. So our sublist is a little inferior to the built-in one. Okay. Now I think is this good? Were these good exercises to kind of get you prepped for the homework for tonight? There's one more. There's actually one more concept that we want to, or one more problem that we want to do, and that is permutation. Now here, you guys, have you ever had a programming assignment where you were to write all the permutations of for example, of a vector, of a one-dimensional array? It's actually not very easy to do. It's quite difficult. But watch how simple it is to do in Prolog. Now, tell me, L1, and here we have this slide, figure 3.5. L1 is a permutation of L. Now, how is it that L1 can be a permutation of L? Let's recall insert. Check this out. Let's do insert A into the list 1, 2, 3, and L. Yeah, I should have reviewed this first. Okay. Now, do you remember how this works? How did insert work? Yeah, anywhere. So first L is A 1, 2, 3, then 1 A 2 3, 1 2 3 A 1 2 3 A, right? And then no. So that's insert. Okay. So now tell me. I'm just writing this down I'm not going to execute it. But tell me this, X vertical bar L. This X vertical, that is a permutation. See, what we want to do is we want to get all the permutations. This is a permutation if what? Well,
if L is the permutation of L without X.
Yeah. Well, to get all the permutations, now let me say it like, to get all the permutations of XL, what do you have to do? You have to put X. You have to insert X into every permutation of L. That's what I'm trying to say. Do you see what I mean? All right. So that's the idea. So actually here, maybe we should demo permutation. So this is called here again. Permutation. My permutation is permutation is built in, so we have to say my permutation. Okay. And so the first version that we're going to do is with insert. So here, let me demo my permutation. So my permutation, and let's do my permutation ABC and then P. All right? So now what should this be? One right after the other. P should do what? It should be all the permutations. Are you with me? So P for one permutation is the original ABC, but then what? Yeah, but can you see that A is going to be inserted into all the permutations of BC? But the first permutation of BC is BC. So what's the next one? BAC and then BCA. Are you with me? But then what? Another permutation of BC is CB. So it's A inserted into CB and then CAB and then to CBA. And then that's it. So did you see, did you see how that worked? So now let's go back to the slide. Right? So what are we saying? What you do is you insert X into the permutations of L1 to get all the permutations of X as the car of L1, as the car of L. Is everybody? So how would you do that? So let's go back to our code. So in our code, what do we have? It's a base case fact and a recursive rule with two conjuncts. So what's the base case fact? What's the base case fact? What's the small here? What's our base case? If we do my yeah, it is. If we do my permutation, the empty list for P, then and so P is all the permutations on the other. What do we get? The empty list. So what's our base case? Yeah, but it's a fact. It's not a rule. So how do you write the base case? My permutation, parentheses what? Empty list, empty list. Okay, so my permutation, empty list. Okay, but on the other hand, now here's what about this XL? So now how do we write the recursive rule with two conjuncts? Say it again. Well, we have to say my permutation XLP if what? First you have to get the what? Is L, let me ask you this, is L bigger than or less than P? Is L longer than or shorter than P?
Shorter than.
It's shorter than. So first you got to get the L.
My permutation.
L, yeah, my permutation has 2.
Yeah.
Okay, so my permutation L1, and so now what is L1? Well, L1 is going to succeed by being all the what?
All the permutations of L.
All the permutations of L. And furthermore, it's going to be one shorter than P, right?
You insert.
And you insert what?
X
Into,
L1 L.
yeah, and insert has how many? Insert is what area? 3. So you insert what?
X L1 L.
XL1P. Are we good? Is everybody with me on this? And notice that what you have to, and the order matters, you guys. You have to do my permutation L1 first because L is shorter. Right? So the order matters. But now look, you guys. Haha. That's with insert. We could just as easily do it with delete. Check this out. Here's a second version with delete. A base case fact and a recursive rule with two conjuncts, but this time instead of using insert, we're going to use delete. Now, what's the base case? Still the empty list, the empty list. But now what? Instead of doing my permutation XL and P, what are we going to do? And then L is smaller than P, what's going to be the my permutation 2? Instead of having peeling off the X from the
My permutation
L, okay, so my permutation L and XP, but now which one is the shorter one? P or L? P is shorter, right? So what do we have? So this time, what do we have to do first? Instead of doing the my permutation 2 first, what do we have to do? Oh, come on, you guys. What does delete? We're going to use delete. How did delete? How did that work? How did that work? Delete. Delete. How did that work? How did that work? Is that how it worked? So now, how do we do this? Delete XL L1, and now which one is the smaller one? L or L1? L1 is the smaller one. So now we do what? Now we make the recursive call to my permutation 2, right? With what? Say it again. Oh, no, we're using delete though. See? Okay. See, before we were using insert. This time we're using delete. So, I mean, you know, we could do it either way. We're doing it with delete this time. But now what is what with X delete, you know? The third one is the second one with the first one deleted. So what has to be true? Sorry, I said that all wrong. Yeah, I was doing delete. So what we're saying is that if L1 is L with X deleted, then what? My permutation 2, now how many arguments does it have? 2. So what is it? L1P, right. Is everybody good with this? Does everybody see how this works? Now, does this help with your whole, I think this way of thinking, I think this is the biggest, this particular assignment is the one where you really have to get your head around this paradigm shift and, you know, try to approach it the way we approached going through these examples right here, okay? Okay, so see you next time.